In this video, I will share an experiment to verify Faraday's law of electromagnetic induction. Suppose a bar magnet is moved towards a coil. As the magnet moves towards the coil, number of magnetic lines of force passing through cross section of the coil goes on increasing. It is observed that a current flows in the coil when the magnet is continuously moved towards the coil. This means an EMF is developed in the coil when there is continuous variation in magnetic flux linked with the cross section of coil. Direction of current gets reversed when magnet is continuously moved away from the coil. The phenomena of development of EMF in a closed circuit when there is continuous variation in magnetic flux linked with cross section of the circuit is called electromagnetic induction. According to Faraday law, the magnitude of EMF developed in a closed circuit due to electromagnetic induction is directly proportional to rate of change of magnetic flux linked with cross section of the circuit. In this case, constant of proportionality K is equal to 1, so EMF is equal to d phi by dt. This is the required circuit diagram for performing experiment to verify Faraday law of electromagnetic induction. A bar magnet is mounted at the middle of a semicircular frame. The semicircular frame is taken to one side and then it is released so that it begins to oscillate freely about the center of diametric arm of the frame. The magnet approaches the coil, passes through it, and then recedes. As a result, magnetic flux continuously varies, thereby producing an induced EMF. The speed of magnet is maximum when it is very close to the coil. So, rate of change of magnetic flux is highest and hence the induced EMF is maximum when magnet is very close to the coil. The deflection in galvanometer G indicates flow of induced current in the circuit. Due to movement of bar magnet in opposite directions, an alternating current is induced in the circuit. The PN junction diode acts as a rectifier and it converts the induced alternating current into direct current. The capacitor C blocks direct current and gets charged. Maximum voltage across the capacitor is equal to maximum value of induced EMF and it is measured with the help of voltmeter V connected parallel to the capacitor C. The resistor R is connected before the PN junction diode for safety of the diode against any excess current. When the semicircular frame oscillates, the magnet mounted at center of the frame possesses simple harmonic motion. So equation of motion of magnet can be expressed in terms of instantaneous angular displacement of magnet theta from its mean position as theta equal to theta naught sine 2 pi over capital T into T. Here theta naught represents maximum value of theta and capital T represents time period of oscillations of magnet. Using the relation between linear speed and angular speed, it can be proved that maximum value of linear speed of magnet is equal to capital R theta naught 2 pi over capital T, where capital R represents radius of the semicircular frame on which magnet is mounted. It is evident that maximum value of linear speed of magnet is inversely proportional to time period of oscillations of magnet. Using Faraday law, it can be proved that maximum value of induced EMF is also inversely proportional to time period of oscillations of the magnet. As both the maximum value of speed of magnet and maximum value of induced EMF are inversely proportional to time period of oscillations of magnet, so it can be concluded that maximum value of induced EMF and maximum value of speed of magnet are proportional to each other. Hence, graph of maximum value of EMF and maximum speed of magnet must be a straight line. Let me introduce the apparatus. This is a coil and this is a bar magnet mounted at middle of a semicircular frame. This is galvanometer. This is voltmeter. These are two PN junction diodes. These are resistors and these are two capacitors. Make various connections in accordance with the circuit diagram. Connect one terminal of coil to galvanometer. Connect the other terminal of galvanometer to capacitor. Connect the other terminal of capacitor to PN junction diode. Connect the other terminal of PN junction diode to resistor. Connect the other terminal of resistor to second terminal of coil. Connect voltmeter parallel to the capacitor line. Move the semicircular frame to one side and note the angle as theta naught. Release the semicircular frame and allow the magnet to freely oscillate until the galvanometer stops showing deflection. When the galvanometer stops showing deflection, press this switch and note maximum value of voltage. Record values of E maximum for different values of theta naught. Note the radius of semicircular frame R in meters and time period of oscillation of bar magnet T in seconds. Using the values of radius r and time period t, calculate maximum speed of magnet for each value of theta naught. Plot a graph of maximum value of speed of magnet versus maximum value of induced EMF. Straight line shape of graph verifies Faraday law of electromagnetic induction. Thank you.